All right, we introduced functions in the last one, domain, range, whether it's a function, and hopefully you agree with me when I say, look, if you've got the picture, then that's quite easy to do. It's when we don't have the picture, okay, now I've got to think about it. So that brings us to sketching graphs. I mean, there are certain basic graphs we should know the shape of just by looking at the equation and go, oh yeah, well I know that's whatever. So some ideas. Basically a graph is a picture of different information that you might have gathered via an experiment or what have you. So it's a graphical representation. So once you have got all that data, then you plot it. So I guess the most basic way of drawing a graph is simply plotting points. And that technique is certainly effective. If you're unsure what it looks like, plot some points and then all of a sudden a shape might emerge and then you'll see what it is. Now, once you've got that, if it's a known function, if you can look at that shape and go, oh, that's a circle, righto, I know what that is, x squared plus y squared's radius squared, or that's a hyperbola, or I know that's basically y equals 1 on x, then it becomes a lot easier to work with. Key things, the consistent scale. So you want the scale to be the same. You don't all of a sudden want to be going along the horizontal axis and at one point one unit is a centimetre apart and then the next unit is 2 centimetres and so on. That's just going to create irregularities in your graph. The scale on the x-axis and the y-axis doesn't have to be. However, it can be useful, certainly if you end up drawing something like a circle. I mean, if your scale's not the same, you're not going to get a circle. You'll end up with an ellipse rather than a circle. But other than that, I mean, you don't have to have the same scale on the y and the x-axis. Known functions. So we're looking for key things. Well, we know the y-intercept. That's probably the easiest point to plot of any graph because that happens when x equals 0. So you substitute 0 into the function, bingo, you know where it cuts the y-axis. X-intercepts, similarly, well, we'll make y equals 0. Now that may or may not be easy to find depending on the equation you end up with. I mean, some equations are difficult to solve. Now once you've found those, any curve's going to be easy to sketch if you know the basic shape of what you're looking at. So you're looking for specific features to work out, all right, what shape am I looking at? As I said before, if you're in any doubt, there's nothing wrong with going back to the very basic idea of plotting points to get a feel for what's this curve doing, what's happening. I guess the most basic function of them all is the linear function, the straight line. There's the most basic of the straight lines, I guess, y equals x. Now, if you see a straight line, then you know what we call a direct variation exists between the data. So direct variation basically means they're both increasing or decreasing for that matter at a consistent rate. But we know anything that does demonstrate a direct variation will create a straight line. So as I say, that's what's known as the linear function. So if you're plotting data and you can see, well, and as you know, when you do an experiment, in real life it doesn't necessarily lie exactly in a nice neat straight line. And so you draw a line of best fit in that situation because there's going to be some experimental error or something like that. So you certainly can approximate the data with that line of best fit. But anyway, back to our most basic equation, y equals x. Every single straight line can be transformed from it. And so it might be a combination of these, translations, reflections, rotations. So how do you recognise it? You may recall y equals mx plus b is a way of writing every straight line. But you'd look at that and go, oh, what do you know? The power of y is 1 and the power of x is 1 as well. So if for some reason you didn't know straight away that's a straight line, you go, oh, that's what I'm looking for. Okay? So terms contain at most one variable and all those variables are to the power of 1. That when we express it with the dependent variable, remember the dependent variable is the y value, as a subject, then we know the coefficient of x turns out to be the slope of the line and that constant number turns out to be the y-intercept. Then there's a couple of special ones. Lines parallel to the x-axis. They all have the equation y equals some constant value because of course the slope of that line is what? What is the slope of a horizontal line? 0. So when we go y equals mx plus b, well m is 0, so we just end up with y equals b. So y equals a constant number. That one goes through the point 32, so we know it's the line y equals 2. And then we have vertical lines parallel to the y-axis. Same idea, you get x is equal to a constant number now. And so I get same point, but so that would be the line x equals 3. So the two special lines, horizontal and vertical, we should recognise those. This sort of question. Show that the point lies on the line. Well, the easiest way to show something is to substitute the numbers in and go, oh look, it works. So let's sub in x plus y is 2 plus 4 is equal to 6. So what I've pointed out there, anytime you get a show that question, might be one like this, but any show that question, is a valid thing to do is simply by substituting the given information. I think the one I'm thinking of right now is like intersectional lines. Right? So they might say, oh, show that these two lines intersect at a particular point. And a lot of people will waste time and go, oh, let's solve them simultaneously and do all that work. When in reality, all you have to do is substitute the point into both lines and go, oh, look, it lies on both lines. Well, therefore, they must intersect at that point. So I show that question, it's a valid way of doing that. So substitute the given information into the expression and any conditions that might be there, and then show that, oh yeah, they all work. So the expression must be true. Okay, so yes, 2, 4, because it does add up to be 6, so it must lie on the line x plus y equals 6. All right, that's the first bit for today.